In 11.2, we learned how to work with means when they were dependent samples. So now we need to think about means when they're independent samples, which is a little bit more tricky just in terms of formulas, if nothing else. So remember, again, sampling method is independent. When the individuals selected from one sample do not dictate which individuals are selected in a second sample, etc. All right, so same thing we've already worked with before. Quick rule of thumb is independent samples are two groups that are unrelated, measured once. Dependent samples are one group, sometimes related, measured twice. Okay. So a study wishes to compare traditional acupuncture with usual clinical care for a certain type of lower back pain. The 241 subjects suffering from persistent nonspecific lower back pain were randomly assigned to receive either traditional acupuncture or the usual clinical care. The results were measured after 12 months. Okay, so this is totally independent. If I have lower back pain and I get acupuncture, it doesn't really have any effect on whether you have lower back pain and are getting, clinical care. Like my pain level really doesn't have anything to do with your pain level, right? We're independent of each other. This is two separate groups, one given the traditional treatment, one given acupuncture. And they're measured one time after 12 months of treatment. And it's a quantitative variable that you're measuring because it's pain level. And we can argue about whether, when you go to the doctors and they say, what's your pain, 1 to 10, and you say it's 5. We can argue about how quantitative that variable really is, but we'll leave that to another day. So it suffices to say for right now, we're going to treat it like it's quantitative. All right, so we want to test whether there's a difference in a body temperature of men and women. So we collect a random sample of 65 women and 65 men and take their temperatures. Again, obviously this is independent because you can imagine that, 65 unrelated males and females, their body temperatures will have no bearing on each other, right? I mean, you meet somebody on the street, you ask them to put a thermometer in their mouth, it doesn't exactly have any bearing on the next person, right? All right, so that would be independent, two groups measured once, and it's quantitative for sure, quantitative. It's temperature. Temperature is quantitative variable. It's quantitative, it's discrete, it's continuous, and it's interval measurement, if you want to recall all that from chapter 1. All right, so now we're going to test hypotheses. And just like before, we have this whole set of criteria that you got to keep in mind. It's on the cheat sheet, so you don't have to memorize it. You need, this time we're going to need independence again. We lost that for a bit. In 11.2, we didn't have independence. And then one of the tests in 11.1, McNamar's test, the second one we learned, the one you have to do by hand. That one is also right here. That one's dependent samples, right? Our example was, do you believe in heaven and hell? That kind of thing. Okay? So when we do this down here, we're working with independent samples. Oops, too far. Come back. There it is. So independent now, which is going to be a little trickier. And they have to be normally distributed, or if your N is large enough, bigger than 30, then you're fine. Remember, bigger than 30 only works when you're working with means. It does not count when you're working with proportions. Proportions don't work like this. That proportions need N times P times 1 minus P to be greater than 10. Let's see right here. N times P times 1 minus P to be greater than 10. So if you don't have that, you're in trouble. But for means, it doesn't work like that. We have our level of significance. Remember, that's your probability of making a type 1 error. You have your hypotheses, but these are with mu's now instead of with proportions like 11.1. And it's not 11.2. 11.2 did the difference thing. It said mu d equals 0, mu d less than 0, that kind of thing. So this isn't doing that. It's doing mu 1 is less than mu 2. There's your test statistic, all there. And then there's your classical approach, your p-value approach. Honestly, as in most things, we'll do p-value more often, especially because the classical approach here kind of fudges some things here. So the author, I think for very good reasons, decides to not really do degrees of freedom. He just has you using the smaller of n1 minus 1 or n2 minus 1 degrees of freedom on the t-table. That's not really degrees of freedom. So computers use a different, and calculators, they use a different degrees of freedom for a problem like this. The real degrees of freedom, and actually there's some issues even there, because you can change higher degrees of freedom is dealt with depending on whether your variances are the same, and it becomes a mess. So the real degrees of freedom, the true degrees of freedom formula is right down here. I put it on the next page just because I wanted to show it to you and show you how god awful that thing is. We are not doing that by hand. We're not putting that in a calculator, none of that. We will have calculators and computers figure stuff out for us, but we're not going to have it do this. So we'll just go with whatever the instructor who wrote the book is, which is the lower of n1 minus 1 and n2 minus 1. But please understand that's kind of a fudge factor. That's not really the degrees of freedom. That's just us getting out of what we have to do but longhand. All right, then the rest of the stuff is all pretty similar. You reject if your p-value is less than alpha and all that good stuff. And then we sweep past that terrible formula that we don't ever want to work with. And we get to down here the body temperature one, which we already said was independent. So we had 65 random females, 65 random males. We set up group 1 to be female, group 2 to be male. No, it did not have to be like that. It just is set up like that. So if you get a setup like this in an exam or something, then go with it. All right, so we have our sample means and sample standard deviations. All right, so we're going to conduct this test using the p-value method with a 0.05 level significance. So we have h0 equal to mu1 equal to mu2, and h1 is mu1 is not equal to mu2. Now, why not equal? Because it says difference right up here. See that? So if it's saying difference, then we're going to do a not equal. Alpha is 0.05. Now, the test statistic. Let me fill this out. Hold on. There we go. There's the big old formula for it. No, you're not going to type this stuff in by hand. That's just silly. But let's enter this stuff in just so we can kind of see what we should have done. So it's 98.394. That's a typo. 98.394 minus 98.105. Those are your sample means, your x bars. Minus 0, because if you say that they're equal in your null hypothesis, then you're assuming that when you subtract them, if they're equal, if mu1 is 98 and mu2 is 98, when you subtract them, you should get 0. So that will be 0 for our course. We're not going to ever muss around really with it being other than 0, but suffice to say you can if in other courses. And then S1 was 0.743. You square it, divide it by 65, and so on. Now, we're never going to do that part by hand. That's just, ugh, no. So we're going to go to StatCrunch and make it do it for us. So you go to Stat. You go to T statistics. Now, in 11.2, we dealt with paired stuff. In 11.3, we deal with 2 sample stuff. And don't forget, this was 10.3, we dealt with the 1 sample stuff. So chapter 11 is either 2 sample or paired. And we're dealing with summary this time. They didn't give us the 65 temperatures for men and 60. We don't have the data. So we only have summary statistics. So we've got to type in our numbers. Let me go back to my notes right here. Bring up my little Java. Okay. So it's 98.394. Sorry, it's so small. I can't make it any bigger. 0.743 for the standard deviation. 65. Then 98.105. 0.699. 65. We will not be doing pooled variances in this course, so you're going to always want to turn that off. We're not going to pool. So unselect that. Click Next. We're doing a hypothesis test. The mean difference was 0, right? Because that's how those computer programs run. And then we're going to do not equal and click Calculate. And there it is. So you can copy and paste it right into your Excel spreadsheet. Oh, but I already did because I've already made this video and it got eaten by my computer. It makes me so happy when that happens. So here's 11.3 example 2 right there. So copied and pasted that in. You can see your test statistic right there and your p-values right there. Always useful. Cool. Alrighty then, let's go back. So you can see the 2.284, which I got right out of there, 2.284. No need to type all that junk in. I'd never do it right on a calculator anyway. Well, I'm kidding. I would do it right, but most people probably wouldn't. Okay, so then step 4, you got to draw that two-tailed distribution. You put your number down, 2.284 on the right, and then negative 2.28 on the left. The p-value got from StatCrunch, it tells you that it's 0.024, and that's both tails. So the StatCrunch already knows it's two-tailed because of the way you selected it, so it knows it's both tails. So you put little arrows and say, hey, these two tails together make 0.024. I know you don't have computer programs to draw it. You've got to draw it yourself by hand. All right, so then we would reject the null hypothesis, right? Because that p-value, which is 0.024, is less than alpha. which means there is enough evidence to support the claim that there is a difference in body temperatures of males and females. Don't know if you knew that, but men and women tend to be slightly different in body temperature. Not by a lot, but a little bit. All right, we're done with that problem. I'll meet you back here for the reading computer output one because that's kind of longer. All right, see you then.